The man who reimagined God's thoughts. In the grand tapestry of human history, there are threads that shimmer with a light all their own. Individuals who arrive as if from another time, another plane of understanding. They see the world not as it is, but as it could be, as its deepest, most hidden laws dictate. They hear a music in the universe that is deafeningly silent to the rest of us. Our story begins not with a name, but with a thought experiment. Imagine you are riding on a beam of light, hurtling through the cosmos at an impossible speed. What would you see? Would the universe stand still? Would time itself cease to have meaning? For most, this is a whimsical daydream, a flight of fancy. But for one mind, it was the key to unlocking the very architecture of reality. He was a man who would challenge a 250-year-old titan of science and win. A man whose gentle eyes saw the invisible fabric that weaves together space and time, a fabric that could be bent and warped by the gravity of stars. He would give humanity the most famous equation in history, a 5-character key to the terrifying power hidden within the heart of the atom. Yet this same man, whose name would become synonymous with superhuman intellect, was once a school dropout, a wanderer, a patent office clerk who scribbled his revolutions in secret notebooks while the world slept. He was a rebel, a pacifist, a refugee, a prophet, haunted by the very discoveries he had gifted to mankind. His journey was not one of effortless genius, but of relentless, stubborn curiosity. A struggle against dogma, against the academic establishment, and against the deepest puzzles of existence. He sought to read the mind of God, and in doing so, he forever changed our understanding of our place in the universe. This is the story of that patent clerk, the dreamer, the rebel who taught us that imagination is more important than knowledge. This is the life of Albert Einstein. Chapter 1. The Compass and the Rebel. Every revolution begins with a spark. For Albert Einstein, that spark was not a call to arms or a political manifesto, but a simple, pocket-sized object given to him by his father. He was just 5 years old, sick in bed, when Hermann Einstein handed his son a magnetic compass. For the young boy, it was an object of pure magic. He would turn it over and over, watching in silent wonder as the needle quivered, possessed by an invisible force, always pointing faithfully north. No matter how he held it, no matter how he moved, something unseen, something pervasive and powerful was guiding that needle. He would later say this experience was one of the most profound of his life. The world, he realized, contained deep, hidden mysteries, and the thought that he might one day understand them filled him with a trembling sense of awe. This burning curiosity was not something the rigid German education system of the late 19th century was equipped to handle. The Luitpold Gymnasium in Munich, which Albert attended, was a place of rote memorization and strict discipline. It rewarded obedience, not inquiry. Teachers saw the young Einstein not as a prodigy, but as a problem. He was quiet, dreamy, and possessed a defiant streak against authority. He questioned everything, not out of malice, but out of a genuine need to understand things from first principles. His teachers, accustomed to students who simply accepted what they were told, found his constant why to be disruptive and disrespectful. One teacher famously told him he would never amount to anything. This environment was suffocating for a mind that yearned to wander through the cosmos. His family life, however, was a nurturing counterpoint. His father, Hermann, and his uncle, Jakob, ran an electrical engineering company. They filled the home with talk of science and technology, feeding Albert's fascination with the unseen forces of electricity and magnetism. His mother, Pauline, was a talented pianist, instilling in him a lifelong love for music, particularly Mozart. For Einstein, music was not a mere hobby. It was another language for understanding harmony and order in the universe. He would often say that his insights in physics came to him not in equations, but in images and musical feelings. The logic and structure of a Mozart sonata seemed to him to reflect the inherent logic and beauty of the cosmos itself. It was this blend of scientific inquiry and artistic sensibility that would become the hallmark of his genius. At the age of 16, the tension between his free spirit and the oppressive school environment came to a head. Using a doctor's note claiming nervous exhaustion, he was able to leave the gymnasium. It was a dramatic break. He wasn't just leaving a school, he was rejecting the entire system it represented. Soon after, he took an even more radical step. In an act of profound youthful rebellion against the German militarism he despised, he renounced his German citizenship, officially becoming stateless. For several years, he was a citizen of nowhere, a wanderer beholden to no flag, only to the laws of physics. His destination was Switzerland, a bastion of liberal thought and home to the prestigious Zurich Polytechnic, one of the few top-tier European universities that might accept a student without a high school diploma. But his first attempt to enter the Polytechnic was a failure. While he scored exceptionally on the math and physics portions of the entrance exam, he failed the general subjects of botany, zoology, and languages. The rebel genius was forced to attend a cantonal school in Aarau, Switzerland, for a year to finish his secondary education. That year in Aarau would prove to be one of the most formative of his life. The school's progressive Pestalozzian methods encouraged visual thinking and individual discovery, a stark contrast to the rigid conformity of Munich. Here he felt free. It was in Aarau, at the age of 16, that he conducted the famous thought experiment that would set him on the path to relativity. Lying in a field, looking up at the sky, he asked himself that fateful question: what would the universe look like if I rode on a beam of light? According to Newton's physics, light should appear stationary. But according to Maxwell's equations of electromagnetism, the speed of light in a vacuum was a universal constant. It had to be the same for all observers. This was a paradox, a fundamental contradiction at the heart of physics. The clockwork universe of Isaac Newton, which had reigned supreme for over 2 centuries, had a crack in its foundation. And the 16-year-old boy, lying in a Swiss field, was the first to truly see it. The seed was planted. It would take him another decade of intense thought to nurture it into the theory that would change the world. Chapter 2. The Patent Clerk Who Dreamed of Light. After finally graduating and entering the Zurich Polytechnic, Einstein's rebellious spirit did not wane. He was a brilliant student, but not a diligent one. He found the prescribed lectures boring and often skipped class, preferring to study the original works of physics masters like Maxwell, Boltzmann, and Helmholtz on his own. He would borrow the meticulous notes of his classmate and friend Marcel Grossmann to cram for exams. His professors saw him as clever but lazy, a charming bohemian who lacked the discipline required for a serious academic career. One professor, Heinrich Weber, was particularly annoyed by Einstein's informal nature and refusal to follow instructions, telling him, "You're a very clever boy, but you have one great fault. You'll never let yourself be told anything." This antagonistic relationship would have severe consequences. When Einstein graduated in 1900, he was the only one in his physics class not to be offered a university assistantship. His dream of a life in academia seemed to be dead on arrival. The next 2 years were a period of deep struggle and uncertainty. Unemployed and nearly destitute, Einstein drifted, taking temporary jobs as a tutor and a substitute teacher. He was adrift, his immense talent unrecognized, his future a blank page. His father's business had failed, and the family was in financial trouble. Hermann Einstein even wrote a desperate letter to a professor begging him to give his son a job, but to no avail. It was a humbling, painful period. The man who would one day be courted by the world's greatest universities couldn't even secure a high school teaching position. Yet through it all, his mind never stopped working, wrestling with the paradoxes of light and motion. It was during this time that he fell deeper in love with Mileva Maric, a fellow physics student from the Polytechnic and one of the few women in her field. She was brilliant and intense, a sounding board for his revolutionary ideas. Their relationship was a passionate, intellectual partnership, but it was also fraught with challenges, including an out-of-wedlock child whose fate remains a historical mystery. Salvation finally came in 1902, thanks to the father of his good friend Marcel Grossmann. He secured Einstein a position as a patent clerk, a technical expert third class at the Swiss Patent Office in Bern. For many, this would have seemed like a crushing defeat, a mundane, bureaucratic job for a mind that dreamed of the cosmos. But for Einstein, it was a lifeline. It was security. And more importantly, it was a blessing in disguise. The work was not overly demanding. He would quickly and efficiently assess the technical merits of patent applications for inventions, and the rest of the day, his mind was free to roam. He called his desk at the patent office his worldly cloister, where he hatched his most beautiful ideas. The discipline of having to analyze and deconstruct other people's inventions sharpened his ability to spot flawed reasoning and get to the core of a problem. In this quiet government building, far from the pressures and dogmas of the academic world, Albert Einstein was free to think. In Bern, Einstein and his friends, Maurice Solovine and Konrad Habich, formed a small, informal discussion group they grandly named the Olympia Academy. They would meet in Einstein's small apartment, feasting on cheap sausage and cheese and debating the great works of philosophy and science long into the night. They read Spinoza, Hume, Poincaré, and Mach, challenging each other's assumptions and sharpening their arguments. This was Einstein's true university. Here, he wasn't a disobedient student or a lowly clerk. He was an equal among peers, a philosopher king exploring the frontiers of knowledge. The academy was an intellectual crucible, forging the ideas that would soon erupt from the patent office and shake the world. It was a testament to his belief that true learning happens not through rote memorization, but through passionate, critical discussion. Meanwhile, his personal life was solidifying. He married Mileva in 1903, and their son Hans Albert was born a year later. He was a family man, a civil servant, living a life of quiet obscurity. To any outside observer, he was just another cog in the machine of Swiss bureaucracy. No one could have guessed that within the mind of this unassuming patent clerk, a series of intellectual explosions were about to occur. He was meticulously dismantling the universe as humanity knew it and rebuilding it from the ground up based on two simple, radical postulates. First, that the laws of physics are the same for all non-accelerating observers. And second, the one that broke everything, that the speed of light in a vacuum is the same for all observers regardless of their own motion. The consequences of these simple ideas were anything but simple. They would lead to a world where time could slow down, where length could contract, and where mass and energy were two sides of the same cosmic coin. Chapter 3. 1905. The Annus Mirabilis. The year 1905 stands alone in the history of science. It is a monument to the power of a single human mind. In the span of just a few months, while working his full-time job at the patent office, the 26-year-old Albert Einstein published 4 papers in the leading German physics journal Annalen der Physik. Any one of these papers would have been enough to secure a physicist a distinguished career. All 4 together constituted a scientific revolution on a scale not seen since Newton. Posterity would call it his annus mirabilis, his miracle year. It was the year the 20th century truly began, not with a bang, but with the quiet scratching of a pen in a small apartment. The first paper, published in March, tackled a puzzle known as the photoelectric effect. Scientists had observed that when you shine light on a metal plate, it can knock electrons loose. But strangely, the energy of these electrons didn't depend on the brightness of the light, only on its color or frequency. A dim blue light could eject electrons where a blindingly bright red light could not. This made no sense if light was a continuous wave, as everyone believed. Einstein made a breathtakingly bold proposal that light itself is not a wave, but is composed of discrete packets of energy, like tiny particles. He called these packets light quanta. We now call them photons. This idea was so radical, so contrary to a century of established physics, that it was met with widespread disbelief. Even Max Planck, whose own work on black-body radiation had hinted at quantization, was horrified. But Einstein was right. He had not only explained the photoelectric effect, he had laid the foundation for the strange and wonderful world of quantum mechanics. It was for this paper, not relativity, that he would eventually be awarded the Nobel Prize. Just a few weeks later, his second paper arrived. This one addressed a seemingly minor curiosity called Brownian motion, the random, jittery dance of microscopic particles like pollen suspended in water. For decades, scientists had been unable to explain it. Einstein, using powerful statistical arguments, showed that this dance was caused by the ceaseless, invisible collisions of individual water molecules. In doing so, he provided the first compelling mathematical proof of the existence of atoms. At the turn of the 20th century, many prominent scientists still considered atoms to be a convenient fiction, a useful theoretical tool, but not a physical reality. Einstein's paper made their existence undeniable. He had made the invisible world of the atom visible through the lens of mathematics, settling a long and bitter debate. Then, in June, came the bombshell. The paper was titled On the Electrodynamics of Moving Bodies. It contained no citations, no footnotes to the work of others. It was a pure product of thought, starting from his 2 simple postulates about the laws of physics and the constancy of the speed of light. From these, Einstein derived a whole new reality. He showed that there is no absolute time, no universal now ticking away for everyone in the universe. Time, he proved, is relative. A clock in motion ticks slower than a stationary clock. A fast-moving spaceship, upon returning to Earth, would find that less time had passed for its occupants than for the people they left behind. He also showed that space is relative. An object in motion appears shorter in its direction of travel. Space and time were not separate, absolute entities as Newton had proclaimed. They were interwoven into a single, dynamic continuum, space-time. This was the special theory of relativity, and it completely overthrew the foundations of classical physics. As if that weren't enough, in September he published a short addendum to his relativity paper. It was almost an afterthought, a 3-page supplement that contained the most profound consequence of his new theory. In it, he demonstrated that mass is nothing but a concentrated form of energy. He derived the relationship between them in what would become the most famous equation ever written. E equals mc squared. Energy equals mass times the speed of light squared. The speed of light, c, is a colossal number, and squaring it makes it astronomically larger. This meant that a tiny, almost infinitesimal amount of mass could be converted into a stupefying, almost unimaginable amount of energy. At the time, it was a purely theoretical insight. No one knew how this conversion could be achieved. But the equation was a cosmic prophecy, a warning of the incredible power locked away inside the nucleus of every atom. It was the secret of the stars, and it would, decades later, become the terror of the world. Chapter 4. The Ascent to Olympus. General Relativity. The miracle year of 1905 had cracked open the door to a new universe. But Einstein knew his work was incomplete. Special relativity was a beautiful theory, but it had a significant limitation. It only applied to constant, uniform motion. It didn't account for acceleration, and more importantly, it didn't include the most ubiquitous force in the cosmos, gravity. Newton's law of gravity, which described an instantaneous action at a distance, was fundamentally incompatible with a universe where nothing, not even information, could travel faster than light. This contradiction gnawed at Einstein. It became his obsession. The quest to reconcile gravity with relativity would consume the next 10 years of his life. A decade of intellectual struggle so intense he would later describe it as the most arduous journey of his mind. The breakthrough came from what he called the happiest thought of my life. In 1907, still at the patent office, he was sitting in his chair when he imagined a man falling from a roof. He realized that for the falling man, during the brief moments of his fall, the sensation of gravity would disappear. If he were to drop objects from his pockets, they would float alongside him. In that falling frame of reference, gravity would cease to exist. Conversely, a man in a windowless elevator accelerating upwards in deep space would feel a force pressing him to the floor, indistinguishable from gravity. This was the principle of equivalence. The effects of gravity are locally indistinguishable from the effects of acceleration. It was a profound insight. Gravity was not a force in the traditional sense. It was a manifestation of the geometry of space-time itself. This idea was the conceptual key, but turning it into a complete mathematical theory was a Herculean task. By this time, Einstein had finally left the patent office. His 1905 papers had slowly but surely gained him recognition, and he finally secured a position in academia, first in Zurich, then Prague, then back to Zurich. He needed help with the formidable mathematics required to describe curved, four-dimensional spacetime. He turned to his old friend, the man whose notes had saved him in college, Marcel Grossmann. Grossmann introduced him to the arcane world of tensor calculus and Riemannian geometry, the only mathematical language capable of describing his vision. For years, they struggled together, filling notebooks with equations, going down blind alleys, facing moments of despair where the problem seemed impossibly complex. Einstein later recalled how he felt he was going mad from the effort. In 1914, he was offered a prestigious professorship at the Prussian Academy of Sciences in Berlin, the pinnacle of the German academic world. It was a move that freed him from all teaching duties, allowing him to focus solely on his quest. It also placed him at the heart of European physics, but it came at a personal cost. His marriage to Mileva had been deteriorating for years, and she refused to move to Berlin. They separated, and the outbreak of World War I that same year left him isolated in a city gripped by a fervent jingoistic nationalism he abhorred. While his colleagues were designing poison gas and artillery, Einstein, a committed pacifist, threw himself into the final, frantic push to complete his theory. He worked in a state of near total absorption, his health failing, driven by the conviction that he was on the verge of a monumental discovery. In late 1915, the race intensified. The brilliant German mathematician David Hilbert, having heard Einstein lecture on his progress, began working on the same problem. For a few terrifying weeks, it seemed Hilbert might reach the final equations first. Spurred by the competition, Einstein entered a final, feverish burst of creativity. In a series of 4 lectures to the Prussian Academy in November 1915, he presented his masterpiece, step by step, correcting errors in his previous attempts. The final result was the Einstein field equations, a set of 10 tensor equations of breathtaking mathematical elegance and profound physical meaning. The theory was complete. It was called the general theory of relativity. What the theory described was a complete reimagining of the universe. Mass and energy, he proposed, do not create a force of gravity. Instead, they tell space-time how to curve. And the curvature of space-time, in turn, tells mass and energy how to move. It's often visualized as a bowling ball placed on a stretched rubber sheet. The ball creates a dimple, a curvature in the sheet. A smaller marble rolled nearby will not be pulled by the ball, but will follow the curve in the sheet created by the ball's presence. So it is with planets orbiting the sun. They are not being pulled by a mysterious force. They are simply following the straightest possible path, a geodesic, through the curved space-time created by the sun's immense mass. It was a vision of gravity not as a force, but as the very geometry of the cosmos. It predicted that even light, which has no mass, should follow these curves, and that time itself should run slower in a stronger gravitational field. A decade of struggle had culminated in a theory of sublime beauty, a symphony of physics and mathematics. Chapter 5. Eclipse of the Sun, Dawn of a Star General. General relativity was a theory of unmatched intellectual beauty, but for several years it remained just that, a theory. It made several concrete, testable predictions that differed from Newton's physics. It correctly explained a small, long-standing anomaly in the orbit of Mercury that had puzzled astronomers for decades. But this was post-diction, not prediction. To truly be accepted, the theory needed to make a novel prediction that could be verified by experiment. The most dramatic and observable of these predictions was the bending of starlight. Einstein's equations predicted that light from a distant star passing near the sun should be bent by the sun's immense gravitational well, causing the star to appear in a slightly different position in the sky. The effect was minuscule, and normally the sun's own brilliance would make such an observation impossible. There was only one way to test it: during a total solar eclipse. The opportunity came on May 29, 1919. A total solar eclipse would pass over a path that included the island of Principe off the coast of Africa and the town of Sobral in Brazil. Despite the lingering animosities of World War I, the British scientific establishment, led by the astronomer Sir Arthur Eddington, recognized the monumental importance of this test. Eddington, a Quaker and a pacifist, was a great admirer of Einstein's work and saw the mission as a chance to heal the wounds of war through the universal language of science. 2 expeditions were organized. Eddington himself would lead the team to Principe, while another team would travel to Sobral. Their mission was simple in concept but fiendishly difficult in practice. Photograph the star field around the sun during the few precious minutes of totality, and then compare those photographs with images of the same star field taken at night months later. If Einstein was right, the stars closest to the eclipsed sun would appear to have shifted their positions. The day of the eclipse was fraught with tension. In Principe, the weather was terrible. Thick clouds obscured the sky all morning. Eddington was in despair. Just as the eclipse began, a small break in the clouds appeared, allowing them to take a few precious photographic plates, though the conditions were far from ideal. In Sobral, the weather was clear, but the primary telescope suffered from a focus issue, blurring the images. A smaller backup telescope, however, managed to capture a set of clear plates. For months, the world waited as the teams returned to England and painstakingly measured the tiny black dots on their glass plates. Rumors swirled. Was Newton to be overthrown? Was the German scientist correct? The results were announced on November 6, 1919, at a packed joint meeting of the Royal Society and the Royal Astronomical Society in London. The atmosphere was electric. The president of the Royal Society, J.J. Thomson, the discoverer of the electron, hailed it as one of the most momentous, if not the most momentous, pronouncements of human thought. Eddington presented the findings. The measurements from both locations confirmed the deflection of starlight, and the amount of deflection was consistent with Einstein's prediction, not Newton's. The room erupted. The news flashed across the globe. The next day, the headlines were sensational. "Revolution in science," declared the Times of London. "New theory of the universe. Newtonian ideas overthrown." Albert Einstein, the obscure German-Swiss physicist, became an overnight global superstar, the first scientific celebrity of the modern age. Chapter 6. An Unwilling Prophet. The 1919 eclipse confirmation transformed Albert Einstein from a respected physicist into a global icon. His face, with its kind eyes, unruly halo of hair, and drooping mustache, became instantly recognizable, a symbol of pure genius. He was mobbed by reporters, photographers, and adoring crowds wherever he went. He was inundated with letters, invitations, and honors from around the world. The public, weary from the senseless slaughter of World War I, latched onto him as a figure of hope. Here was a man who transcended national borders, who dealt not in the petty squabbles of politics, but in the eternal truths of the cosmos. He was the high priest of a new scientific age, and people projected onto him all their hopes for a more rational, peaceful world. Einstein was a deeply private person, and he found this sudden, intense fame bewildering and often burdensome. He called it the circus. Yet he also recognized that it gave him a platform. He decided to use his new global pulpit to champion the causes he believed in. He was an ardent pacifist, speaking out against militarism and compulsory military service. He was a committed socialist, critical of the inequalities of capitalism. And he became a vocal supporter of Zionism, not from a religious standpoint, he was not a practicing Jew, but from a cultural one. He saw the need for a homeland where Jewish people could live and cultivate their identity free from the persecution they had faced for centuries in Europe. His political activism, however, made him a controversial figure. His fame and his Jewish identity made him a prime target for the rising tide of anti-Semitism and right-wing nationalism in his native Germany. The Weimar Republic was a fragile democracy, and many conservatives and nationalists resented the new order. They saw Einstein's relativity as Jewish physics, an example of corrupt, non-Germanic thinking. An anti-relativity movement was formed, funded by reactionary industrialists. They held rallies denouncing Einstein and his theories, mixing scientific criticism with vile anti-Semitic slander. Philipp Lenard and Johannes Stark, both Nobel laureates in physics, became leaders of this movement, promoting a so-called Deutsche physics that was supposedly based on experiment rather than abstract Jewish theory. It was a dark and ugly perversion of science in the service of racist ideology. At first, Einstein was amused by his critics, but as the attacks grew more personal and threatening, the danger became clear. His name appeared on extremist hit lists. When the Nazis came to power in 1933, Einstein was visiting the United States. He knew immediately he could not return. He was a public enemy of the new regime. The Nazis ransacked his home in Berlin, confiscated his bank account, and publicly burned his books. A Nazi publication featured his picture with the caption, "Not yet hanged." Einstein, the man who had renounced his German citizenship as a teenager and then regained it to join the Prussian Academy, was once again made stateless by the country of his birth. He found a safe haven in the United States, at the newly formed Institute for Advanced Study in Princeton, New Jersey. He would spend the rest of his life there, a refugee from the tyranny that was consuming Europe. From his quiet office in Princeton, he worked tirelessly to help other Jewish scientists and intellectuals escape the Nazi regime, writing affidavits and using his immense influence to secure them positions in America. He had become more than a scientist. He was the conscience of his generation, a symbol of intellectual freedom standing against the tide of barbarism. The unwilling prophet had accepted his role, using his fame not for personal gain, but as a shield for the powerless and a weapon against injustice. Chapter 7: The Bomb and the Conscience. In the quiet town of Princeton, Einstein hoped to return to his solitary work on the mysteries of the universe. But the world would not let him go. In late 1938, German chemists Otto Hahn and Fritz Strassmann made a terrifying discovery. They had successfully split the uranium atom. The news of nuclear fission spread like wildfire through the physics community. Physicists everywhere, including the many refugees who had fled Europe, immediately understood the implications. Einstein's own equation, E equals mc squared, now had a clear, practical, and horrifying path to application. The immense energy locked within the atom could be unleashed. A bomb of unimaginable power was now theoretically possible, and it was Nazi Germany that had made the key discovery. In the summer of 1939, a group of concerned Hungarian refugee physicists, led by Leo Szilard, became convinced that they had to warn the American government. They feared that Hitler's scientists were already working on an atomic weapon. But who would listen to a small group of foreign scientists? They needed a voice with authority, someone whose name would command immediate attention at the highest levels. They needed Albert Einstein. Szilard and his colleague Eugene Wigner visited Einstein at his summer home on Long Island. They explained the chain reaction, the possibility of a bomb, and the danger of Germany developing one first. Einstein, the lifelong pacifist, was stunned. He had never imagined his theoretical work would lead to such a weapon. "I never thought of that," he reportedly murmured. He understood the terrible dilemma. His pacifist principles recoiled at the idea of creating such a weapon, but the thought of Hitler possessing it exclusively was a far greater evil. Reluctantly, Einstein agreed to sign a letter. Drafted primarily by Szilard, the letter was addressed to President Franklin D. Roosevelt. It calmly and clearly explained the scientific situation and warned of the extremely powerful bombs of a new type that could be constructed. It urged the U.S. government to take action, to secure a supply of uranium ore, and to accelerate experimental work in the field. The letter, delivered to Roosevelt in October 1939, was the spark. It set in motion a chain of events that would ultimately lead to the creation of the Manhattan Project, the massive, secret American effort to build the atomic bomb. Ironically, Einstein himself played no role in the project. His pacifist and socialist leanings made him a security risk in the eyes of the FBI, who had a thick file on him. He was not given the security clearance to participate in the work he had inadvertently helped to start. He spent the war years in Princeton, a figurehead kept on the sidelines, largely unaware of the scale and progress of the operation at Los Alamos. Then, on August 6, 1945, the world changed forever. Einstein was at his summer home when he heard the news on the radio. An American atomic bomb had been dropped on the Japanese city of Hiroshima. His secretary, Helen Dukas, recalled that he simply said, "Oy vey," a Yiddish expression of profound woe. In the aftermath of Hiroshima and Nagasaki, Einstein was consumed by a profound sense of guilt and responsibility. He would later call signing the letter to Roosevelt the one great mistake in my life. Though he knew the bomb would likely have been developed without his letter, he felt the moral weight of his involvement. He dedicated the rest of his life to campaigning against the monster he had helped unleash. He became a tireless advocate for nuclear disarmament, world government, and the peaceful control of atomic energy. He warned that humanity was at a precipice. The power of the atom had changed everything save our modes of thinking, and thus we drift toward unparalleled catastrophe. His words were a desperate plea from the man whose name was inextricably linked to the atomic age, a plea for humanity to find the wisdom to control its own terrifying creations. Chapter 8: The Final Quest and a Fading Light. In his final decades at Princeton, Albert Einstein became something of a living monument. The Saint of Princeton, as some called him, he was a familiar sight, walking to and from the Institute for Advanced Study, clad in a rumpled sweater, his famous hair now a brilliant white. He had reshaped humanity's understanding of the largest scales of the universe, but he was far from satisfied. There was one more mountain he felt he had to climb, one final, all-encompassing theory he desperately sought. He dreamed of a unified field theory, a single set of equations that would unite his theory of gravity with the laws of electromagnetism. He sought a master equation, perhaps no more than an inch long, that could describe all the fundamental forces of nature. It was a quest for the ultimate simplicity, the final thought of God. It was a lonely quest. The mainstream of physics had moved on, charging into the bizarre and counterintuitive world of quantum mechanics, the very theory he had helped to launch with his 1905 paper on the photoelectric effect. But Einstein could never accept the core tenets of the new quantum theory. He was deeply troubled by its reliance on probability and randomness. The idea that the behavior of a particle was fundamentally uncertain until it was measured struck him as philosophically abhorrent. This led to his famous, long-running debates with the Danish physicist Niels Bohr. Einstein would devise clever thought experiments to expose what he saw as the incompleteness of quantum mechanics, to which Bohr would always find a rebuttal. It was in one of these debates that Einstein made his most famous declaration of scientific faith: "God does not play dice with the universe." Bohr famously retorted, "Einstein, stop telling God what to do." This intellectual schism left Einstein increasingly isolated from the new generation of physicists. They revered him as a historical figure, the man who had built the foundations they now stood upon. But they saw his search for a unified field theory and his rejection of quantum mechanics as the quixotic obsession of an old man who had been left behind by the very revolution he had started. He was aware of this isolation. He once wrote, "I have become a lonely old fellow, a strange, isolated old man." Yet he refused to give up. He believed that behind the apparent chaos and probability of the quantum world, there had to be a deeper, deterministic reality, a hidden order that his unified theory would reveal. He would work on the problem until his dying day. In April 1955, his health, which had been fragile for years, finally failed. He suffered a ruptured abdominal aortic aneurysm. He was taken to Princeton Hospital, but he refused surgery. "I want to go when I want," he said. "It is tasteless to prolong life artificially. I have done my share, it is time to go. I will do it elegantly." He worked on his equations in the hospital, his mind still reaching for that final theory. On the night of April 17th, he mumbled a few sentences in German, but the nurse on duty didn't speak the language, and his final words were lost to history. He died in the early hours of April 18, 1955, at the age of 76. By his own request, his cremation was a private affair. His ashes were scattered at an undisclosed location to prevent his grave from becoming a site of morbid pilgrimage. But there was one macabre postscript. During the autopsy, the pathologist on duty, Thomas Harvey, controversially removed Einstein's brain for study, hoping that science could one day unlock the physical secrets of his genius. For decades, the brain went on a strange journey, kept in jars, sectioned, and sent to researchers around the world. It was a bizarre final chapter for a man who cared so little for his own physical vessel and so much for the universe of thought within it. The true legacy of Albert Einstein was not in the gray matter of his brain, but in the ideas he gifted to the world. Epilogue: Echoes in Space-Time. Albert Einstein's search for a unified field theory was ultimately unsuccessful. He never found the master equation he sought. But the quest for such a theory of everything, continues to be the holy grail of modern physics, inspiring generations of scientists who follow in his footsteps. And the theories he did complete continue to resonate through science and culture in ways he could have never imagined. Your GPS navigator works by making relativistic corrections. Time literally runs faster for the satellites in orbit than it does for us on the ground. And without Einstein's equations, the system would fail within minutes. His theories laid the groundwork for everything, from nuclear power and solar cells to black holes and the Big Bang. Even a century after he conceived it, general relativity is still bearing fruit. In 2015, 100 years after he finalized the theory, scientists at the LIGO Observatory made a landmark announcement. They had directly detected gravitational waves, ripples in the fabric of space-time itself, created by the cataclysmic collision of two black holes over 1 billion light-years away. It was a discovery that won a Nobel Prize, and it was the final, triumphant confirmation of Einstein's incredible vision. He had seen it all in his mind's eye a century before we had the technology to prove him right. The man who dreamed of riding a beam of light had correctly predicted the shuddering of the cosmos. But his ultimate legacy is perhaps not in any single equation or theory. It is in the spirit he embodied. He taught us that the universe is not just stranger than we imagine, it is stranger than we can imagine. He showed us the power of the thought experiment, of childlike curiosity, of questioning authority and refusing to accept dogma. He was a testament to the idea that the greatest breakthroughs come not from accumulating facts, but from seeing the world with fresh eyes. His life reminds us that within a single, curious mind, there can exist a universe of possibilities waiting to be discovered. And that the most powerful force in the universe is not gravity or the energy of the atom, but the relentless, boundless, and beautiful power of human imagination.